Welcome everyone to our very first live stream. We are going to be covering vector databases today. My name is Neil Canungo. I'm your host, and I'm joined by Michaela Woods. Michaela, do you want to say hello?
Hi, guys.
So we have an exciting session today. We are kicking off the first of many live streams. We just launched our KDBI Cloud Starter Edition last week. And with that, we want to get you all hands-on into using vector databases, understanding how they work, how to make use of them, and to solve some business challenges. So today we are going to cover a very core use case, which is document search in vector databases. So this is a nice light introduction to vector databases, and we'll be doing some unstructured data querying and finding relevant text for our documents using KDB AI. Now, with this session, you can actually follow along with us. KDB AI is free to get started with. So you can go to kdb.ai and you can sign up. So with that, let me walk you through how the sign up process works. So as we get started here, you can go to kdb.ai in your browser. There's a free sign up in the top right. And that will allow you to create a free account where we're going to show you how to download the sample exercise and follow along with us in your own instance. So as I'm talking through this intro, if you want to go ahead and get signed up, you can get your whole account ready. And when we kick off with Michaela's demo, you'll be able to follow along. So again, you go to the sign up on the top right, and then the next thing is you'll have some basic information that you enter to set up your account. So you fill out the form, and then you'll get an email to verify your email address. When you click on that email, you'll be taken to a screen where you hit a button, and then that will start launching your instance, and you'll get one more email that has the link to the sign in page and the login page, and that will take you to this type of dashboard, this console where you'll be able to create new API keys. You'll be given an API endpoint, and that API endpoint you can use with up to 3 API keys that you can manage. You can create and delete them. Now, when you do create an API key, it's good to copy that somewhere to like a notepad or something, because once you create it and view it for the first time, you're not going to be able to view that API key again. So keep that in your records. But then you should be good to go. And Michaela's going to show how to set this up with a Python environment so that you can follow along. So with that, we're going to go to on KDB AI, there is a learning hub, and there's a sample called document search. So as you're signing up, be sure to go to this page, go to the document search sample, and there you'll be able to download the Jupyter Notebook from GitHub. So it's a download at the top of the page. So that is how you get everything set up. Now, if you don't want to follow along with doing the exercises yourself, you're free to just listen in. Let us know you're here. Say hello to us in the chat. We'd love to hear from you and know that you are enjoying the session. So we will cover this as a hands-on tutorial, but you can also just listen in. So before we get started in the session, I know vector databases are new to a lot of folks, and what I wanted to do is go over just some basics of how vector databases work, so that you have some good context for what we're doing in the session. So with that, let me go to my next slide on vector database introduction. So vector databases. So what you're going to see here in this diagram is a process where you're going to take source data, and this can be structured or unstructured data. Now, typically vector databases are used a lot with unstructured data that is passed through an embedding model, often a deep learning model. That creates a vector, a structured format. You're taking this unstructured data and you're creating a structured format that's stored in the vector database. Now, this structured format actually captures, I'm going to go into this a little bit more in the next slides, but it's a vector, and it captures the semantic meaning of your unstructured text. So maybe it's a story, and it's capturing the writing style, it's capturing the era, it's capturing the protagonist. Maybe it's a video and it's capturing what the video is talking about. And typically, this was all done with keyword searches. So you had to historically tag your data with keywords that search engines could find. But now, what's really cool is that vector databases allow you to search by semantic meaning. So much like how humans find information. If I asked you to tell me about some music you like that was in the 80s, you might think of some different genres, or like maybe in the 90s, you might think of some grunge rock or some hip hop, or you have some sounds in your head. You could actually search by these semantic meanings rather than tagged audio or tagged video or tagged documents, images, things like that. So that makes sense. We're really like adding a lot more context to what search is capable of, and it's truly revolutionary. And what it's allowing is powering generative AI applications. It's powering better search results. It's making use of the majority of data that's created today. Over 80% of data created today is unstructured data, and we're able to make use of that better. So the data is going to be stored in a vector database, and you perform a query, and that will give you some results that you can then put to post processing. This will refine your results, re-rank your results, filter your results, basically give you what you need depending on what your application is, and it'll feed it back to your application. Now, the application is where the end user sits. They're the ones submitting their query. The query goes through an embedding model and lands in the same format, a vector format, goes into a vector database, and kind of comes around in this loop. What this does is really extend the knowledge and memory of AI, so the knowledge base that AI has access to. A lot of models like ChatGPT, you might see, are limited to the to like September 2021. That's when all the data for ChatGPT was trained on, and you can't get data that's after that date. But what vector databases do is they allow you to then work with large language models or other applications and find more data that you can then feed back into your large language models, extending to your organizational data, more real-time data, more up-to-date data, improving your search. So that all works through an application, query, vector embedding, vector database, and post-processing. Now, one thing I want to point out is the vector embeddings and the embedding model do happen outside the vector database. We're going to show how to create vector embeddings, but with the vector database, you're expected to bring your own embeddings into the vector database, and that's what you will search. Okay, so let's talk a little bit about what are vectors and how these vector embeddings work. So a vector is simply something in space that has both magnitude and direction. So it needs to have at least 2 points, or it needs to have like a magnitude and direction. A single point can't have direction. So in 2 dimensions, going to the point 1, 1, we see this vector. And going in 3 dimensions, we see it as this other vector. Now, you can't really visualize 4 dimensions or 5 dimensions or 6 dimensions, so you have to kind of use your imagination there. But these vector embeddings can be thousands of dimensions long. So they're actually like very high dimensional space. And you get to choose how many dimensions that you want in your vector embedding. The more dimensions you have, the more detail you're capturing about your source data. So that's the basics of how a vector works. But the cool thing about using a vector is it really opens us up to a lot of vector math, similarity searches, cosine similarity, Euclidean distance, things like that we'll go into in a second. So vector math allows us to find nearby vectors in our vector database. So the process of creating an embedding is you'll take a data object and you pass it through an embedding model, and that'll create a vector for you that is, again, in high dimensional space. These are vector embeddings. Now, the vector embeddings in the embedding model, the embeddings that come out depend on the model you use. And the model may be an audio model, a text model, a video model, an image model. Different models will produce different embeddings. There's hundreds of different types of like document models and sentence transformer models, and we'll go over that in a second in Michaela's section. But the different embedding models is important to pay attention to. That is going to create your vector embeddings, and that will depend on the type of data you're using. And that will put these vectors in vector space. So imagine each of these little dots are vectors in your vector space in a higher dimensional space. And then you'll ask a question of it, and a query will land in your vector space. So you'll get a query vector. The query vector goes through the same embedding model that the query vector is generated by going through the same embedding model that you use to store your data and create your original embeddings. So if you had a human query, like what's the differences between apples and oranges, that would go through the embedding model, and then that would generate what you're seeing here as a structured, high dimensional numerical representation of that question that machines can easily understand. So when that query vector lands in vector space, it will be mapped to all the nearby vectors, and all, depending on the type of search you're using, you can select, do you want the 3 nearest vectors in Euclidean space? Do you want the 3 nearest vectors in cosine similarity? There's different similarity metrics, but essentially you're selecting the nearby vectors. And why this is also really powerful is because traditional search works through exact matches, but what you have with vector databases are approximate matches. So you're able to find data that's related to your query, but doesn't have to be exactly tagged like your query. So that opens up a lot more contextualization for your search results. There are 3 types of similarity metrics used in KDB AI. There is cosine similarity, which just looks at the angle between the vectors. There is Euclidean distance, which looks at magnitude and the angle, magnitude and direction, and dot product, which looks at magnitude and direction. And you'll use different similarity metrics depending on your application. So, for instance, if you are looking at some plagiarism detector or a document search, and you want to find similar documents, one document might be highly related to document A, might be highly related to document B, but document B might be twice as long. And so for that context, like if you want to find 2 documents that are related but are totally different lengths, you might use something like cosine similarity that doesn't look at the magnitude, but does look at the direction. So the 2 documents would be oriented in the same direction in the vector database. And so what this does is, as an example, you'll give it a query like show me documents about AI. You may have a few different documents in your vector database, and this will find 2 vectors with 2 vector embeddings that are similar to each other, and it will find those documents and return the context for you that you want. And you don't have to return the whole document. You can return just parts of the document that are relevant to your search. And so an example with an image example, we have like an MRI scan that goes through a embedding creation. So the image goes into the embedding, out comes a vector embedding that's stored in KDB AI. That gets stored, all the different images get stored as vectors. And then as the application and user searches, they'll search the KDB AI vector database and find the relevant images they want. So for find similar MRI scans, they can find where there might be tumors or healthy brains or healthy scans, things like that, looking at similarity search. So with that, let's go ahead and jump into our hands-on tutorial. And Michaela, I'm going to hand it over to you, and I'm going to bring your screen on. And why don't we go ahead and get started? Thanks.
Cool. Thanks, Neil. Yeah, so I'm going to go through a practical example of what Neil just explained. And hopefully anyone who wants to follow along was able to follow the instructions that Neil laid out at the beginning to get your own copy of the notebook I'm sharing right now. What we're going to do here is we're going to start by loading and splitting a PDF document. So otherwise, splitting can be known as chunking, and it's a crucial step ahead of running semantic search on text data. Then we're going to create some vector embeddings, like Neil explained. Then we're going to store these embeddings in our KDB AI vector database. And then we're finally going to run semantic search to retrieve similar records. So as Neil said, feel free to ask questions in the chat throughout, and we'll do our best to answer them as we go or at the end. Okay, cool. So there's some setup steps needed ahead of time here. I'm just going to start by running these and get them downloaded. The first one here is just how we're going to load our PDF. We've got a library for that. We've got Spacey, which is how we're going to split our document. Then we've got some libraries for creating our embeddings. So sentence transformers is our one of choice, and I'll go through why we're choosing that later. Then we've got our libraries needed for the vector database, the main one here being our KDB AI client, which allows us to talk to KDB AI. We're loading in specific Spacey English corpus here, which is what we'll do to how we're going to split our document, as I mentioned. Just configuring the console and defining some helper functions, and then we're ready to get started. So before I dive into loading in the document, I just want to reiterate there about what we mean by semantic search, and obviously Neil kind of went through it there already. So we're really converting our query into vector representation and then finding similar vectors in the database rather than exact matches. So we're going to load in our document to start off here. This is using this PyPDF2 reader and just concatenating that all into one document. And then we come to splitting the text into sentences. So in this snippet of code...
Sorry, I'm going to just jump in right there. I know you're right in the middle of a thought, but we did get a question on what's the link of the notebook. If you can just go ahead and show the Learning Hub real quick.
Yeah.
So on KDB AI, you go to the Learning Hub at the top, and you can go down to the samples with the document search and download on GitHub the notebook that you can get started with. So, yep. So there's the Python notebook there. Yep. So sorry for interrupting. Go ahead.
No, I'll keep on interrupting. That's fine. So yeah, the PDF we'll use, by the way, I didn't mention that either. We have it linked here. It's a research paper on interstellar object populations. So just about the amount of objects that are in the Milky Way, which I thought was interesting, or interesting enough to demonstrate similarity search. So in this snippet of code here, we've just, as I said, read the file. Then we're splitting it up here. So this is how we're referencing our Spacey chunker, or how we're splitting our data into sentences. And I think I'm missing, maybe one of my packages didn't load up the top properly. Just leave that for a few seconds to run before I reference it here, sorry. So yeah, we're applying this Spacey model here, which is a pre-trained model for English text processing. So it does it based on linguistic rules and patterns in the text. So not just looking at where there's full stops or exclamation marks, it's a little bit more advanced than that. There are many different ways to chunk text. You don't have to do it into sentences. Depending on a lot of different factors actually will be how you determine how to chunk your data. So for example, we're going to use a sentence transformer model in the next step to do our embeddings. If you're using a different embedding model, you might decide to chunk your data differently. The size of your input. So again, we're just doing quite a simple example here of one PDF, but if you have a huge corpus of text, or say many books by different authors or something like that, you might want to chunk it maybe in paragraphs instead of sentences, or do a more complicated chunking method. And then as well, taking into consideration what your expectations are for how you'll use this when you come to do the querying. So are you just doing a quick semantic search query, or do you want to integrate with something like a large language model to do question and answering, summarizing the data from your documents? So we'll actually see that in a different example we have on LangChain, and I'll just quickly show that near the end of the
And I wanted to add to that, a key reason for chunking when you're working with large language models is that you have context windows, which are token limits on what you can enter into a large language model. So even some of the newer large language models like Claude 2 have 100,000 token limits, but a book like Moby Dick is a few 100,000 token limits. So if you wanted to ask a question about Moby Dick, you actually couldn't put that whole text into your prompt. And even if you could hit that 100,000 token limit in your prompt, it'd be a really expensive prompt. So what's more desirable is to instead pull out relevant chunks of data, relevant chunks of information from your vector database and inject those in the prompts. And that's a little bit how retrieval augmented generation works and LangChain, which Mikhail will go over at the end. But what we're just showing is that core piece of pulling that relevant text out in chunks. And as she described, there's many different strategies for chunking. Yeah.
Great. Yeah, thanks, Neil. And you can see here what we're left with is a number of different sentences. So if we just index into the first one, we see this is like the top of the document. So looking at here, we're just getting like the title up here. If we go to an index a little bit further down here, you'll see this is like a sentence. So we have our different sentences now chunked up, ready for embedding. So as I said, we're going to use a sentence transformer model. There's over 100 different types of sentence transformer models available, so you can check them out on Hugging Face here. Depending on the training data that's used to train them, that's why there's so many different ones. We're using this all mini LM L6 V2 one, which is a pretty popular one that people use. It's quite good at doing sentence embedding as well, and works for chunks of sentences that we've kind of created here. And it's quite good for semantic search as well. So we've chosen it here. Again, if you say have proprietary documentation with a lot of, or maybe not so much in the form of text, but maybe you've got images that are, say in a case of like scan images in a hospital, you might choose to pre-train your data with your own model if you want to get more accurate results here. But for the case that we're looking at here, which is text, this should give us pretty good results using this public version. So we're able to grab the model we want here, referencing it using the sentence transformer library. Then we use model.encode here, and this is the bit that's actually turning that raw text from the sentences into a vector. This is what Neil went through in his diagram at the start. And just to say as well, on Learning Hub, we do have a section on articles. So if any of this is new to you, do check out these articles here. We have one specifically on vector embeddings, which shows what Neil kind of went through at the beginning in a lot more detail. So if you're interested in learning more, I definitely recommend checking that out at the end or afterwards. So we've created our embeddings in this code snippet here, and then we're just converting it into a pandas data frame, which is easier for the format that's going to go into our KDB AI database. And once we show this data frame, it's just going to take a few seconds to run the model here, we'll see that it has two columns. So the first one there was the vectors. See, that's come back now. So you see these are the vectors we've just generated. And then we're also storing a second column called sentences with the raw text here. We can add many more columns here if we wanted. Say, for example, we have many different research papers, different authors. You could add an authors column, and that's really handy actually, because later on you can do filtering while you're doing your semantic search. Say you wanted to filter on a particular author's documents only, you could do that. For this example, we've kept it simple, but yeah, just to note, you can add extra columns here, which makes filtering easier later on. It also means you can easily tell if your search result is accurate, obviously being able to see what the raw text returns. And these are our sentences that we had a look at earlier up the top, obviously saved down now as vectors. Yeah, so one last thing to note just on the embeddings, it's important to note the length of our vector, so how long this here is. We can just use len to find that, and ours is 384. And this will come into play in the next section where we're defining our index. So knowing your dimensionality of your vector is important, and this is what Neil showed at the beginning. So you can have two-dimensional vectors, three-dimensional vectors. In our example, we have a dimension of 384. Obviously, that's hard to represent diagrammatically here. But yeah, just to that's what that number is actually meaning. Okay, great. I think we're ready to store our data in KDB AI. I think hopefully some of you guys were able to connect to KDB AI and get your URL endpoints and keys.
There were a couple questions. So just before we jump into this next part of the demo, just Arun Kumar was asking, how long is the trial lab environment available? There is no end date. So this is a free edition. So you can just sign up and get going. And then Philippe was asking, what's the difference between KDB and KDB AI? So if you're familiar with our time series database, KDB, this is maybe a big question that you have. Like KDB AI is our vector database with similarity search and vector indexing. KDB is our time series database that is also vector based, but it doesn't have the same similarity search and some of the features that we're showing here. So that's the difference.
Yeah.
Yep.
And just to add to that, like KDB is still our core product, and actually KDB AI is built on top of it. And people have been using KDB to do things like vector similarity search, but they've had to build a lot of the libraries and integrations themselves. So KDB AI aims to make that easier for users as well.
Yeah. Thanks. And there was a question about recording. Yeah, this is actually going up on our YouTube. So make sure to subscribe to our YouTube channel to get these recordings and watch them in perpetuity as you need. So
great. So the next step needed here is connecting to our KDB AI session. So I have mine open here. If you've been able to log in, you should see something that looks like this. What you're going to need is your URL here and your API key. So if you don't have one, you can just click generate and copy and paste that in. And when you run this cell, you'll be prompted to enter both your URL and API key. And then once you've run that, I've done it before here. We can see if we run session.list with an open and closed round bracket, that actually returns if we have any tables saved in KDB AI. So we don't, which makes sense because we haven't done anything with this instance yet. But that's just a nice way to check if we're connected or not. Okay. So now that we're connected, we're going to define a table schema where we are going to save our embeddings. And we want this to look the same as our data frame that we have up here. So we're going to have two columns, vector and sentences. And you can see here we're defining sentences. We're just making that a string. And then when we're defining our vector columns, this is when we specify our index. So there's a few things that we need to pass in here and be aware of. The first thing is dimensions. So this is where we checked that length of the dimension. I'll just scroll back up again here. We've seen it was 384. So if you're using your own data, you need to be aware my dimensionality needs to be defined and match what my schema is saying. The second thing here is metric. So this is referring to Neil's slide on the different types of metrics there is available. So whether it's cosine, Euclidean distant, or dot product. L2 here is Euclidean distance, which is the one we're using in this example here. And then the type here finally is the type of index. So there's a number of different FICE or FAISS Facebook similarity indexes available. So we have HNSW, IVF, IVFPQ, and flat indexing methods. So depending on which one you want to try or use, we're just going to start with the NSW one here today. It's pretty good at performing semantic search on text data. And it's pretty the performance is pretty good. It doesn't do an exhaustive search like something like flat would do, but it does yield pretty good results in pretty fast time and low memory usage.
So we have a pretty comprehensive article in the Learning Hub. If you want to jump to that real quick, there is a
point. Yeah,
there is an indexing basics article, and this goes through flat, graph, and inverted file indexing. And at the very bottom of this article, it actually shows what scenarios you might want to use different indexing methods. But we'll leave that for you to investigate and if there are any questions on it, we're happy to answer them at the end of the session.
Cool. So yeah, we're using our metric of L2 and HNSW. So let's just define our schema. There's just a cell here just checking if I already have that table defined on KDB AI. I don't, but there's no harm in running it just in case. And then finally, we're getting on to where we're creating our table here. So we're going to call it PDF, and we're going to pass the PDF schema. And once that's run, we can then query to see if our table is there. And what we should see is it exists, but it's empty because we haven't added our embeddings data yet. So that's run now. Let's query. And we see we've got our 2 column sentences and vectors, and they're empty. So let's fill our data in. We're passing in that data frame from above that we prepared earlier. And then if we requery, we can see now the data is saved and persisted down to KDB AI. So that's it. Our data is now in KDB AI. If we wanted to check that on here, we could refresh our cloud and see my table is now showing up, and you can tell the index, the distance metric, the dimensions. So if you're working with multiple tables, this can be useful just to check the status of them. And once that's loaded, we're ready to do our semantic search. So first, we need to embed our search term using the sentence transformer model. So you want to use the same model that you used to get your vectors into this format in the first place. So I think Neil had a slide on this as well. Maybe we don't need to jump back to slides for everything, but it was useful to see here. So this is kind of our query. We're doing this using the same embedding model to get a numerical representation again. And that's important, obviously, to be querying like with like. So we're going to pass this question or statement in, number of interstellar objects in the Milky Way. If we execute that, we're going to run our model on it to encode it into numerical embeddings. And then we're going to run table.search here. And this is searching our KDB AI table. And we're asking for the 3 nearest neighbors back. So if we wanted to get more than 3 back, you could change that number. And we see we get the table return that looks like our KDB AI table with 1 additional column, which is the nearest neighbor distance. And this is the Euclidean distance or L2 similarity measure. So you can see here, we've got varying degrees of similarity coming back. So if we look at like the actual sentences themselves, they're kind of truncated here. So I'm just going to change the call width on my Jupyter notebook just to extend that a little bit and just index into the sentences themselves. So if we asked about the number of interstellar objects, we can see the first result is kind of listing some of the authors, and then it does say something about the Milky Way hosting a huge population of interstellar objects. That's okay. But in the second sentence, it's saying something similar. And I don't think it's to the third sentence till we get the actual answer we're looking for. So it's saying interstellar objects 52. So that's obviously came back third. So our model is okay, but we needed to look a few levels down to get them with similar result. But hopefully you can see that by being able to query with an approximate term, maybe we wouldn't have found this in the document as easy by just searching for exactly what we're looking for. And we can show this maybe again with a different search term. So I'm asking, how does planet formation occur here? We're going to encode that again and do the same thing. So running our similarity search, the nearest neighbors distances here are better. So we would hope this is a more accurate result. So if we just look at these sentences, we can see the populations, dominant, dynamical formation I shouldn't have picked a paper with so many big words. Mechanisms would preferentially harvest more distant, ice-rich planetesimals from the disks of solar systems. So that sounds like it's answering a question on how does planet formation occur. And I think the second one and third one are similar. So that's good. I think they're reasonable results. It's a great start, but I think the next step might be feeding these results back to a large language model, for example, to do some prompt engineering and basically provide a summary answer of this in a more natural language form and human readable form so that it's easier for us to digest. And that's actually the basis of our LangChain sample. So if I just hop back to the Learning Hub and we go to this LangChain example, this does a similar thing. We're starting with a document, in this case, a text document, but it works in a lot of the same ways. I'm not going to go into this in too much detail because we do have a LinkedIn Live coming in a few weeks, specifically for this sample. But this should look quite similar, except some of the main differences are we need to load in various line chain libraries, and for data preparation, remember we used the spacey model to chunk our data into sentences. In this one, we're going to use this recursive character text splitter. So rather than splitting it into sentences, we're going to split it into chunks of 500. And this works well when we're using LLMs at the endpoint, and also where you're going to use OpenAI embeddings, which works better on fixed length of chunks of fixed length rather than varying lengths of different sentences, for example. So depending again on what your data is like, what you're going to use it for at the end, you might choose to use different chunking methods. So I just wanted to point out this is an example where we use a different one. Steps the rest of the way through are very similar. We're connected to KDB.ai again. We're storing our data, so I'm not going to spend too much time on that. What I wanted to show is where we're connecting the result with an LLM. So we've shown here both OpenAI and Hugging Face. And when we pass in the query, we're able to print a response from OpenAI, and it's using the document that we've passed it, and it's summarizing it. So rather than just getting exact matches back, we're getting a nice sentence back that's obviously summarizing the results. And then we can see here, we've gotten varying degrees of detail from the different LLMs, which is interesting.
So I think just to like emphasize this point, this is so that what you're seeing in the lane chain and retrieval augmented generation RAG sample is a document that was on Obama's State of the Union address. And so a natural question is like, what are the nation's strengths? And you're getting a natural response, an OpenAI response or a Hugging Face Hub response. The OpenAI responses tend to be, we find them to be a little bit more rich. But you can choose your different LLM that you want to generate a response. And this is likely if you're just doing pure documents, conversational interfaces, you would probably want to use something like this. If you just want to pull those chunks out of relevant sentences, you do the first part, which Michaela was showing, which is kind of like the predecessor to this lane chain example. This is just showing pulling the relevant sentences out. The conversational interface comes through the LLM.
Yeah. So you can see really how integrating with LangChain and different LLMs really extends the functionality of what your vector database can do on its own. Yeah, so that wraps up the tutorial and the sample. I think the last step here is just deleting the table when you're done. So I think we can go to some questions, maybe if we have some time. Neil, if there's any in the chat.
Yeah, we had a few questions and some really good ones. So one from Jeff was asking about like other vector databases and what are the main differences between them. And Harry was asking about the standard databases like Redis or Postgres and implementing similarity functions. And this is a question we get often. Michaela, if you can go actually to our homepage on KDB.ai, we have outlined. So in our initial launch of KDB.ai, we have KX has a really strong pedigree in temporal analysis, and with that, we have introduced 4 temporal differentiators that you'll see here: relevant, time-aware, comparable, and real-time. So what this means is you're able to do point-in-time analysis in search and retrieval. So if you want to see how like trends are changing over time, you can do that with KDB.ai. It's comparable and it's time aware. So comparable is like if you have multiple windows of search and you want to see how those 2 windows are comparing to each other over time. And then the time aware part or the relevant part is, let's say you're asking a question about what's the best smartphone. Well, that might pull the best smartphone from all time, or it could pull the best smartphone from the, that's currently out today. And so what people, big challenge with LLMs is finding that the documents and the data that are most relevant to the search query based off of recency, based off of semantic characteristics. What KDB.ai does is allow you to pull the more recent information first and have finer results or more refined results. It's also capable of billion vector search, so it's highly scalable. I mean, KDB has been around for a couple decades. We have a strong history of, we have a strong database engine. What we, like Kyla said, we're building on top of KDB that we've had available for quite some time. We've just made some easier functions for you to do similarity search. So this is a native vector database. There are native vector databases out there. Some are like Weaviate, Pinecone, Qdrant, and they have different advantages and different disadvantages. Native vector databases are tending to perform better from my research compared to things like Postgres, which, yes, you can do similarity search with Postgres, but when you start to load a lot of embeddings in there, it tends to start to fall apart. We have the #1 ranking on DB engines, something that Paula mentioned in the chat. So I thought I'd highlight that. So, and Michaela, feel free to pull that up if you want the DB engines ranking on vector databases. So we have a highly scalable database with a lot of governance features, a lot of security features that you'll get to experience. And again, this is just our initial release of KDB.ai, so we're going to have even more and more differentiators going through there. So yeah, if you go to the DB engines ranking at the top left, or yeah, there you go, right there. So KDB is well above the competition in terms of vector database management systems. So yeah, stay tuned for our further developments in KDB.ai. It's a great tool to get started with. What we're showing now is just some basic fundamentals of how you use a vector database to work with your data. We do have, when you sign up, you will get access to our Slack channel, and you can get real-time responses from our experts in KDB.ai. Mm-hmm. If you want to start loading in your own data, you want to start experimenting with different things, we're here to help you. Slack channel is a great place to get, again, real-time responses. Anything else you want to add to that, Michaela?
No, I think that's good. I think we just had a question there come in. Are we building on top of the Q language or Python?
Yeah, so my understanding is that it's Python abstracted on top of Q. So Q is masked. You're not having to write Q code. You can write all in Python code, but it's using the Q engine for those that are familiar with KDB.
Yep.
Okay, great. Well, that kind of wraps it up for today's session. We do have another session next week. We're going to aim to do these every Wednesday for the next 6 weeks or 5 more weeks. Next week, Nathan Crone is going to present on building a music recommender. Really cool use case there using vector databases. And we will have a few more sessions. So September 27th is a music recommender. We're going to do image search. That MRI example will show you how to kind of assist in healthcare practices, but you can use this for any type of image search to find similar images, dissimilar images. We'll do our LangChain one in mid-October, sentiment analysis one, and pattern similarity. So, Wednesdays, 8:30 a.m. Pacific. I think it's 4:30 p.m. UK. Yeah. So try to find the best overlap between our time zones. Michaela's based in Dublin and I'm based in Seattle. So
it's tricky sometimes.
Yeah, tricky sometimes. Early mornings for me, late afternoons for her sometimes. Yeah. But yeah, we have some more sessions coming up. So follow us on our LinkedIn channel, our LinkedIn page, follow us on YouTube, and keep an eye out for these new sessions. The music recommender session is live for registration now. Thank you all, and have a great rest of your week.
Thanks, guys. Bye.